So, Sophie, a few people escaped to get some coffee, so we're rousting them, and we're going to bring them back in.
Sure. It's been a long week. Let them have coffee.
Okay, so as streaming people are streaming back in, I'd like to introduce our last speaker with a story. So Lean's Mathematical Library is maintained by the Lean community, a grassroots organization, which has a team of maintainers that's tasked with, maintaining the library and, merging pull requests and so on. And the maintainers recognize that it's very helpful to the project when notable accomplished mathematicians begin using Lean and take an interest in it. And so on the maintainer stream, there's actually a thread called VIP alert, when somebody shows up that we're excited about. So our next speaker, Sophie Morel, was one of our first VIP alerts. So in 2021, in early 2021, I believe, so this was in the heart of the pandemic, the heart of the lockdown, when we were all stressed out. There was a lovely online meeting. It was our first Lean for the Curious Mathematician. It was like this. It was a week-long, talks and tutorials, but focused exclusively on Lean. And it worked remarkably well. I mean, we had kind of people doing Lean exercises in breakout rooms, and people going from room to room to help them. But Sophie was there, so that was where I first, saw her online. But before the meeting, shortly before the meeting, word went out that Sophie Morel had appeared on Zulip, and then word went out that Sophie had registered for the meeting, and then, if I remember correctly, like a week or so later, word went out that there was Sophie's first pull request, a contribution to MathLib, was issued, and it was very much. Like when you see the Elvis documentaries, when they have the security in an Elvis concert, on the walkie-talkies saying, Elvis has entered the building, and Elvis has left the building. So Sophie, I don't know if you if you were aware of all the excitement, about your presence, but again, for a lot of us a lot of us in the Lean community, it really was a milestone and a landmark, and it was good news at a time, during the pandemic when we really needed good news. So it's nice for me to finally have an opportunity on behalf of a lot of us to thank you for that, and also thank you for speaking us today. So Sophie, please take it away.
Sure. Can you hear me? Okay.
Yeah, we can. The volume is a little bit low, but yeah. So yeah. Go ahead.
Oh, okay. I can. I'm not sure I can do anything.
Yeah, it's perfect now. Our technician raised the volume, so you're perfect.
Oh, okay. Great. So thanks for the introduction. I'm really, really, really embarrassed. No, I knew nothing about that. Obviously. Okay. And so I'm going to try to keep this as non-technical as possible. And so I wanted to talk about using Lean to help you with your own research. So let me just go through a few definitions. So fortunately for me, I'm the last speaker, so you all have met Lean by now, so I don't have to go through the Lean introduction that Flores had to do. So it's an interactive theorem prover, and you use it to formalize mathematical statements and formalize their proofs. And in particular, you can use it to check the validity of the proofs, which is very reassuring. And Lean is, I think, well, I get asked regularly, since I'm French, why is ROC not more popular with mathematicians? It was here before. And I say, well, Lean has, I guess, a good PR team, mostly Kevin Buzzard. And it has this big mathematical library. So if you want to start working with Lean as a mathematician, it's slightly easier because you don't have to formalize all these basic results that are in the library. Or I didn't switch to BI, it doesn't matter, I guess. Okay, and well, as we saw in Flores's talk, there are many, many collaborative projects to formalize some mathematics in Lean. I'm actually in a couple of them. And that's not what I want to talk about today. And these projects are, they're very useful. Not only do they give some new theorems that other people can use, but they usually you also get new insights from them, maybe simpler proofs, more general statements, a better point of view. Okay, but as I said, Flores already talked about that very well. So what I want to talk about today is can you use Lean in your own research? So suppose you're writing a paper and you have some exciting new math, but this is exciting to you. Can you use Lean to check the new math that you're writing? And the answer is obviously yes, because it's been done many times. So here I have a list that has no pretension to exhaustivity. So there's a few examples where people, maybe with the help of a couple of Lean experts, formalize some of their own papers or part of their own papers. And then, well, I had to mention the liquid tensor experiment, since that's, I think, the most famous such example, where a very, very recent and very advanced result of Clausen and Scholze was formalized by a team of 18 people over a year and a half. Okay, so, well, something about that list is the first three, so the first two papers are in combinatorics. The third paper, it's, the whole paper is not formalized, they formalize the combinatorial arguments. And the last one, well, the last one is, so it's not combinatorics, but the last one, it took 18 people, and it took them a very long time. And suppose that you don't have, I mean, you're not Peter Scholze, you can't just, you have this paper, you have this couple proofs, you're not totally sure, you've checked them many times, but you're not totally sure. You can't just ask all these people to spend all that time on your proofs. So what can you do? And suppose also that your field is not, well, it's something that is a bit, well, not yet in MathLib. The basics are not yet in MathLib. So my field, for example, is arithmetic geometry, Langlands program, automorphic forms, and we're starting to have some algebraic geometry in MathLib. But it's going slowly. So obviously, I mean, there are a few solutions. You can change fields, but like maybe you don't want to do that because maybe you chose your field because you liked it. You can also help develop MathLib, which is a very good solution, but it's very slow. So what else can you do? So I wanted to talk about some ways I try to still use Lean. Okay, so a couple observations about that. First, you're not going to be able to check everything. So you're not even going to be able to formalize every statement in a paper. So you have to choose, which parts of your papers you want to try to formalize. And the second observation is this is not a formalization project like Flores talked about, or like the liquid tensor experiment. You don't want to spend a year on a paper, so maybe you're going to have to admit results from the literature. So sorry, I'm guessing if you did the Lean tutorial, you know what sorry is. Sorry is just a way to admit something in Lean. Okay, and so I want to talk about, well, some experiments I had with that and what the pitfalls were, how they turned out, and what the problems were. Okay, so the first experiment is actually, well, I said I work in arithmetic geometry, but even I sometimes write papers in combinatorics. So here's a paper. How's the font size? Okay.
Well, it's a little bit small. We can see algebraic combinatorics. That's
Yeah.
better. Yeah.
Well, I mean, so the point is not, of course, to have you read the paper. So this is a paper that's in algebraic combinatorics, inspired by some arithmetic geometry, but it's entirely in algebraic combinatorics. And this paper, so the main result in this paper is something about the Coxeter complex of the symmetric group. It says something like there's certain type of subcomplex of the Coxeter complex of the symmetric group, and it says it's shellable. So I just want to talk a bit about what's involved in that. So shellability, that's a property of abstract simplicial complexes. So I'm guessing not everybody knows what an abstract simplicial complex is. So let me just kind of give you a flavor of that. You will see a formal definition in Lean on the next slide, I think. But it's a purely combinatorial object, and it's kind of so you have this thing called the geometric simplicial complex, which is this geometric object that you get by gluing simplices along their faces in this very simple way. So you just match faces together and glue the simplices like that. And an abstract simplicial complex is kind of a blueprint for one of these geometric objects. So it only contains the information of which simplices you are using and how you glue them together. But it doesn't tell you where you put them in space, how you arrange them in space. It's just this information of which simplices, how they're glued. And it's they're not in MathLib because somebody, by which I mean me, is pretty bad at, well, despite what Jeremy said, I'm not very good at doing pull requests in MathLib. So they're not in MathLib, but it's very easy to define them in Lean. So here's the definition. So an abstract simplicial complex on the type alpha. So it's just a set of what we call faces, and those are finite sets of elements of alpha. So in Lean, we say it's a set of the type fin set alpha. So fin set means finite sets with elements of type alpha. And then you want every face to be non-empty. And then you want, you want, if you have a face, then every non-empty subset of it should also be a face. So if we go back to our example, for example, I could take here, the first one, I could take alpha to be R3 if I think of this as a subset of R3. And then the faces are the sets of vertices of the simplices. So this dots here. So every face, every one of these fin sets here is just the set of vertices of one of the simplices here. So for example, I can have the 4 dots that are the vertices of the tetrahedron, that's a face. And then all subsets of these, all non-empty subsets are going to be the set of vertices of one of the faces of the tetrahedron. So they should also be in our abstract simplicial complex. So that's says a very simple definition. And then shellability is, well, it's easy enough to define in Lean too. Well, I haven't defined everything in this code, but it's there's something about how you can build the abstract simplicial complex by adding the facets. The facets are the maximal faces. So by adding the facets one by one in a nice way. So maybe so the point is not really to tell you what all this is, but just to show you, like, it's very easy to write the definition. And here I fell into the first danger. The first pitfall is the temptation to formalize the background theory. So instead of just being satisfied with this definition of abstract simplicial complexes, definition of shellability, I wrote a full library of abstract simplicial complexes, so it took a couple months. That's not what you want to do. I mean, if you want to do what I was outlining at the start of the talk. Okay. So that was abstract simplicial complexes. So if we go back to the paper, I said it says the Coxeter complex, or some subcomplexes of the Coxeter complex are shellable, including the Coxeter complex itself, but that was known before. So I talked about shalability, abstract simplicial complexes. What is the Coxeter complex of the symmetric group? So it's a poset, and its elements are ordered partitions of the integers from 1 to n. So that means a partition is just a decomposition of this finite set into non-empty subsets that are mutually disjoint. We call them blocks, and ordered partition. So that means that the blocks are given in a specific order. So for example, the partition 1, 2, 3, 4 is not the same as 3, 4, 1, 2. And then the order is just an ordered partition is smaller than an ordered partition P is smaller than an ordered partition P prime if P prime refines P. And when you refine, you have to take the order into account. So here I put some examples. So hopefully that's clear enough. So for example, here, the last one has unordered partitions. This partition with blocks 3, 1, 2, and 4 does refine this 1, 1, 2, and 3, 4, but the refinement is not in the correct order. So I can't just merge the blocks while respecting the order in the second one to get the first one. So that's the Coxeter complex. The smallest element is the partition with only one block. And then you have a bunch of maximal elements, which are, there is one of them here, 2, 1, 4, 3. They cannot be refined further. So that's the ordered partitions where the blocks all have size 1. And that is the same as permutations on this finite set of integers from 1 to n. So that's where the symmetric group shows up. And here, so I'm telling you this is the Coxeter complex. The Coxeter complex is shellable, and that doesn't make sense because the Coxeter complex is I defined it as a poset. It's not an abstract simplicial complex. An abstract simplicial complex was this, set of subsets of some alpha such that blah, 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 some properties. And so we actually stated it like that, here's the Coxeter complex, here is some sub-poset of it, it's shellable. Well, actually, we didn't state it like that. We actually gave the shelling order, but okay, so what's the problem here? So something is implicit in all that, and what is implicit is the following. So if you have an abstract simplicial complex, then you can look at its faces, so these finite sets, and they are ordered. They form a poset for inclusion. Okay, and this poset uniquely determines the abstract simplicial complex, of course, up to isomorphism. And then these posets of faces of abstract simplicial complexes, you can characterize them among all posets. So they are the ones where all intervals are Boolean posets, and then they are what's called mid-semi-lattices. Anyway, they can be characterized intrinsically. And the Coxeter complex, if you remove the smallest element, which would be some empty face, which is not allowed. So if you remove the smallest element, the Coxeter complex actually satisfies those properties. And so the Coxeter complex is the poset of faces of an abstract simplicial complex. And all the properties that we consider, so shellability in particular, are invariant by isomorphisms of abstract simplicial complexes. And this, we actually do say it in the paper, but it's like a one sentence in, maybe can find it somewhere. I don't know if blah, 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 all the partitions, blah, 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 blah. I don't even know where we put it. So here, recall that, so this is the poset that I call the Coxeter complex. Recall that this is a joint semi-lattice. Oh, I said mid, okay, it should have been joint. Where each interval is isomorphic to Boolean algebra, hence is the face poset of a simplicial complex. So it's in there, some remark, oh, by the way, and then we state a bunch of theorems that all refer to abstract simplicial complexes. Never mention this again. Okay, and there is no reference, by the way, to this characterization of phase-pole sets of simplicial complexes because this is a well-known fact. So who needs a reference? Oh, and yeah, I just wanted to show you an image. This is what the simplicial complex looks like in the case of S4. So the Coxeter complex is n-1 dimensional as a simplicial complex. So it's, if you know what a permutohedron is the dual of the permutohedron. But this is just, well, so you have a visual representation, but that's not my point. So my point is that actually I went too fast. So if you're trying to formalize this theorem, then if you just look at the statement of the theorem, it doesn't make sense. And Lean is not going to, I mean, the first problem is like you say, I have this object, it satisfies that property, but the property is defined for a different kind of object, and there is a bunch of like unsaid stuff to make the statement make sense. So you could think, okay, well, to actually prove the statement, I will need to be able to actually construct the abstract simplicial complex whose phase-pole set is the complex, and then they have some concrete realization of it that I can manipulate. And that's not too hard. I actually did it in Lean. However, you can also just reformulate the theorem because the definition of shareability actually only uses the order relation on phases, the inclusion that's given by inclusion. So you can just state the main theorem without going to abstract simplicial complexes at all. But this is not what the paper does because this is not what is natural if you're an algebraic combinatorist. Okay, and we talked about, formalization and auto-formalization and the challenges of auto-formalization. And one of the challenges that was mentioned for auto-formalizing statements is that, well, sometimes the statements, there are several ways to write them in Lean, and it's not obvious to human that they are equivalent, but it's not obvious to Lean, and it's a very hard problem to actually show, automatically that they're equivalent. But this is another kind of challenge. The statement just doesn't make sense. If you're not a human who knows the field, the statement just doesn't make sense. Okay, so that was the second pitfall. Sometimes mathematicians just notice that some things are the same, but it's not obvious. Even if you're trying to formalize the paper and you're not from the field, that's not obvious to you. And of course, it's even less obvious to Lean. Okay, and so that was the first project, and that was actually done. It took me about 3 months, but that's because I wanted to formalize every background result. And I wasn't really in any doubt about the correctness of the proof, actually. So I just wanted to learn a little bit more about Lean. Now, the second project, I actually had some doubts about some proofs. The second project is about another paper, so I'll show you the other paper. It's on arXiv. Actually, it's been accepted to Documenta, but it's not formally published yet. I mean, it's not, yeah, anyway. So that's a 79-page paper, and just look at the title. If you know a little bit what the objects are, you're going to see that this is absolutely not formalized. In Lean, it deals with schemes of a number of fields and these things that are sheaves for the Etel topology, except they're Lydic sheaves, so it's even more complicated, and then they're actually perverse sheaves, and then it's just like, it's not in MathLib yet. Okay. So it's totally out of reach to formalize the whole paper. It's totally out of reach to formalize the statements. However, in this paper, there's a paper again, there's an appendix. And the appendix here is actually totally categorical, well, except for the application part. But this is like 12 pages here that are purely categorical stuff. And this appendix actually cost me a lot of pain. That paper took something like 14 years to be accepted. Well, because I'm very lazy, but also because it came back several times from the journal with the referee saying, but you wrote this thing and it's not quite correct. Okay, and so when I finally got to this last version, okay, so I just wanted to mention that, so this appendix, there was a hope that it would be possible to formalize it, or at least some parts of it, because the category theory library of math is pretty well developed. It's the homological algebra part. So I want to mention that I'm using the work of Joël Rioux a lot here. He really put a lot of homological algebra in Mathlib, and he has even more homological algebra on a publicly available repository that hasn't been PR to Mathlib yet, but that you can still use. Right, and so I said what I was starting to explain, why did I want to formalize this? Because I wrote a lot of wrong stuff in this. At the beginning, this wasn't an appendix, this was just some subsection in the paper. And it was pure abstract homological algebra, and I wrote a few things that were wrong, so I was trying to do stuff that is a bit non-standard. So if there are any experts in the room, it was like deriving functions between a billion categories, but they were not left exact or right exact. There are no injectives, there are no projectives. It's not clear. It's not totally clear what you should do. It's I was trying to use in categories, pro categories. It was awful. And every time the referee said, well, there is a part I don't quite understand. Okay. And at the end, I wrote this 12-page appendix, and I think now I got it right. It took me years, but I got it right. But I wasn't really sure of myself anymore because I had written so many wrong things about that. And so I wanted to check it. I really wanted to check it, even though the referee was satisfied. I wasn't satisfied. So here I'm giving you the link to the project. And right, so I want to talk a little bit about the special challenges of formalizing category theory in particular. Well, not just category theory, some mathematics, including category theory. So I call this part Know Your Enemies. And the first enemy is the word canonical. Have you read really in a lot of algebraic fields, the word canonical is overused by some people, including me. Actually, here's a little experiment. Let's search for canonical. 48 occurrences in this paper. Canonical. So that's a lot. And I've tried to identify its meaning. So I found 3 possible meanings. So the first meaning is something that was constructed without making arbitrary choices. I don't want to tell you how it was constructed, but I want you to know that there were no arbitrary choices. So here I'm giving an example. The map from vector space to is bidual. So you can't find, I almost said canonical. I'm trying not to use canonical anymore. It's really hard because I'm so used to it. So if you want to construct an isomorphism, a linear isomorphism between a vector space, a finite dimensional vector space, and its dual, you have to make choices. You have to choose a basis. And then that gives you a dual basis, etc. But if you want to go to the bidual, you don't need to make any choices. There is a map. There is a linear map that doesn't depend on choices. And I put the definition here on the slides. So we like to call it canonical. And the second, so those are not necessarily mutually exclusive, by the way, these meanings. The second meaning is that thing is uniquely determined by some properties. I might tell you what they are, or I might not tell you what they are. And for example, I've heard people say, well, the local Langlands correspondence for GLN is a canonical bijection between this and this. And then if you ask them, they say, oh, well, it's uniquely determined by like the compatibility of L and epsilon factors and compatibility with local class field theory, blah, blah, blah. Okay, so that doesn't matter for this talk. Well, what does matter is I've actually heard somebody call, call the local class field isomorphism canonical, and if you're a number theorist, you know that's a big lie because actually there's the choice of a sign somewhere, and there is no choice that is better than the other. So sometimes canonical is used where it shouldn't be used. Okay, and the third possible meaning that I wanted to mention is in Bourbaki. So Bourbaki actually defines canonical, but in Bourbaki, canonical is just an adjective that you put on well, some list of things that you don't want to introduce notation for them, but they're important enough. So, okay, here's the example. For example, if you have two sets, you can look at the Cartesian product and you have projections. So from the Cartesian product of A and B, for example, to A, just send a pair AB to its first entry. And so that's the first projection, it's called. But maybe you don't want to give, I mean, you might want to call it like P1 or PA, but maybe you don't want to give it a name. So Bourbaki just writes for the ages, trying to write all of mathematics from the beginning. And maybe they want to be able to use P1 for another purpose later. So instead they say, well, we're going to call this the canonical projection from A cross B to A. And then when we say the canonical projection, well, readers should know that it's something that we introduced before and decorated with this adjective canonical. Okay, and Bourbaki is actually pretty careful about that. So if you see something called canonical in Bourbaki, it means that when it was introduced, there was some sentence that said, we are going to call this canonical. However, there's some problems with that. First, if you're not careful, there might be several ways to interpret something as canonical. Okay, I didn't find an example, but exercise maybe. And if you're not Bourbaki, Bourbaki just writes this list of books that depend on each other. If you're not Bourbaki, then it's not clear what previously introduced as canonical means. It's not well defined. Anyway, something like Lean is not going to understand. Something like Lean is not going to understand the Bourbaki definition either. In Lean, you just have to give a name to this. You give a slightly longer name, maybe. Doesn't matters. It matters less in name that the names are longer. And then there's a secret force meaning is just canonical means something that I find natural. And if I go through the paper, I'm trying to here it says the derived category will always canonically equivalent. So this is meaning number one, there's some construction that is a natural construction, but I'm not telling you what it is. And I think they all, yeah, so canonical is they all appear somehow, like meanings 1 and 2 are not exclusive. Canonical isomorphism, that's our second enemy actually, this expression canonical isomorphism. I read this paper and I was just ashamed at how many times I used canonical isomorphism. Canonical T structure is an example of the third meaning. Actually, there is a T, it's the name of T structure is some kind of object and a construction category theory, and this is just the name of one of the T structures. It's just called the canonical T structure. So this one is the only one that's fine, I think. All the others. Canonical projection, that's also this, that's the second projection, I guess. So this is also an example of the Bourbaki meaning. Can we use, this is a canonical map. Oh God, yeah, no, the canonical isomorphism. Anyway, so second enemy, that's the equality sign. So this is in category theory specifically. Kevin Brothers has talked a lot about how equality is more complicated in type theory maybe than in set theory, but that's not even what I want to talk about. I want to talk about the way the equality sign is used in category theory. So in category theory, when you have these things called objects, like maybe they are sets, maybe they are groups, and then maybe they are vector spaces, and you have these things called morphisms. That's just the maps between them that preserve the structure. And you never want to say that two objects are equal. Well, first, because most of the time it's not true, and it's not relevant. What is relevant is, do they have the same structure? So is there a bijection between them that preserves all the structures? And yeah, I'm only talking about concrete categories. If you are category serious, I apologize. But that's just trying to get my meaning across. But there is this, well, the equality sign. So we shouldn't write equalities between objects. It's just evil. But the equality sign is used to denote canonical isomorphisms, whatever that means. And I want to give an elementary example that doesn't mention categories. So that's the free abelian group on a set. So that's a simple example of a universal construction, of which there are a lot in category series. So if you take a set, you can imagine it's a finite set. And a free abelian group, so it's an abelian group A, such that we're giving a morphism from A to some abelian group B is the same as giving a map from X to B. And of course, you try to formalize that, but if you just think about it, this doesn't make sense. What does the same mean? It doesn't mean anything. So what actually I wanted to say is that, well, it's an abelian group A, and it's a map from X to A, such that restricting along this map, precomposing with the map is injective, but we don't need to say that. It follows from the property. So this map, and if I precompose with this map, so that gives a bijection for every abelian group B. It gives a bijection from morphisms of groups from A to B to maps from X to B. So if I have a morphism of group from A to B, say I call it U, I look at U composed with iota, that's a map from X to B. So that gives me this arrow here, and this arrow is bijective. So every morphism of group, what did I say? So every map from X to B arises from a morphism of groups, and two morphisms of group that are equal on the image of iota are equal. Okay, so that's a perfectly reasonable definition, and here are some possible constructions of this object. So for example, you can take functions with finite support from X to Z. So if X is finite, that's just functions from X to Z. If X is not finite, that means the functions have to be zero outside of a finite subset of X. And then the abelian group structure is just like pointwise addition of functions. And iota, you just send X to the indicator function of the singleton X. And that does satisfy the universal property. Another construction, you can take the non-commutative free group on X. So that's just reduce words on the elements of X and their inverses. And reduce means that if you have an X followed by an X minus 1, they cancel each other. So you shouldn't have an X followed by an X minus 1 or an X minus 1 followed by an X. Anyway, so that happens to be a group. The operation, the multiplication is just concatenation, and then you have to make the word reduce. After you concatenate, you might have this x minus 1 patterns appearing, and you just remove them. Anyway, so you have this non-commutative free group, and then you can take its abelianization. So you just take the quotient of these by the subgroup of commutators. And then iota, well, you send an element of X, you send it to the word X in the free group, and then you send it to its class in A. And that's another, that's also is going to satisfy the universal property. And these two objects they're not the same set. I mean, if even that makes, I mean, in set theory, we would say that things are the same set, but unless you do your constructions in a very strange way, they're not going to be the same set. But as they have the same properties as abelian groups, so we want to say, oh, they're canonically isomorphic. Okay, so what does that mean? So here's just that's just the definition of a free abelian group on X again. So what it means is a free abelian group on X And you notice I keep slipping, I keep saying the free abelian group, even though it's not unique, but it's unique up to unique isomorphism. So what does that mean? It means if we have two of them, like in the previous slide, they're isomorphic. Okay. And the isomorphism is unique. Wait, that's obviously false, because what am I doing here? This A here that I define, it has automorphisms. There are isomorphisms from A to itself. I mean, even if X is a singleton, the free abelian group is just isomorphic to Z itself, and Z has automorphisms. Just sending n to minus n is an automorphism of Z as a group. So when I say unique up to unique isomorphism, it's also not a precise statement. What I mean is it's unique up to unique isomorphism that preserves the extra structure of this iota. So it's the true statement. We have two free abelian groups, A and A prime, with iota and iota prime. There is a unique isomorphism of groups from A to A prime. That satisfies this property that iota prime is phi composed with iota. And then, so in this situation, when you have these two big objects defined by the same universal property, some people would just write A equals A prime because they are canonically isomorphic. And when I say some people, I mean I have done that. Again, not proud of it, but I have done that. Okay, so that's the second problem. The way the equality sign is used in category theory is well, it's hard to interpret if you don't know all the context, because it means there is an isomorphism between the objects that is canonical, and canonical means basically it respects every structure that I want it to respect, but maybe I won't tell you what the structures are, and maybe it's not even clear to myself what the structures are. So here, maybe I'll give you an example. I don't want to, okay, so this is a book on triangulated categories, and this is a great book. Like, I don't want to say that anybody is bad for doing that, because I said I'm doing it myself. It's just, it's everywhere. So, okay, so none of these words make sense, and maybe they're not big enough. But, okay, what I want to talk about here is this. So triangulated functor, here, it's used as a, well, if I was talking in Lean, is used as if it was prop value. It is used as if it's a property. It's actually an extra structure on this object F. That means it says that F, well, it's written here. So F commutes with this sigma that is called the shift, but that's not true, because these are like object type. The properties are like the properties of objects. You can't write an equality. This is actually an isomorphism. So the extra structure is the structure of an isomorphism between F sigma and sigma F. So he's writing it as an equality, and then he goes to this G that has some relation to F, and that, by the way, is also a universal property. G is also only unique up to unique isomorphism, blah, blah, blah. And then he says, well, from this property of F, I deduce this property of G, but that's also not a property, that's also an isomorphism. And actually, the sentence is telling you how to construct this isomorphism, but what the rest of the proof is not telling you is that once you have this isomorphism, you write a bunch of what we call commutative diagrams, and there are compatibilities to check, and he's not checking them. And he's not even mentioning them. And he's not doing that because they're like obviously true. And I mean, this lemma is actually formalized in Lean, and yes, all the compatibilities are true. This category series actually have an intuition about these things. But, well, I mean, if you're not a category theorist, the statement of the lemma itself, again, the statement is not precise, because the statement is G is a triangulated functor, but being a triangulated functor is not a property, it's an extra structure. And the extra structure is actually constructed at the beginning of the proof. So that's the problem if your auto-formalizer is trying to auto-formalize this statement, it will fail because the statement is not self-sufficient. Okay. Well, and also I wanted to show an example of this very casual use of the equality sign. Yeah, I say I think that's wrong, but I've done it too. So sorry about that. Yeah. Okay. So coming back to the project, I had this appendix that was this on here, and now I have all the canonicals. Right, there's an appendix here, and it has these 4 sections. So the 4th section is applications. It's not formalizable at the moment. And the first 2 sections are just a review of some results from the literature with, well, no proofs or just very, very short proofs if you have to put 2 results together, explaining how in the first section, the 3rd section contains some new results. And so what I wanted to do, I just set myself a challenge, was just like formalize enough definitions and statements from the first 2 sections so I could just fully formalize the proofs of the 3rd section. And did that work out? Well, it's not so easy. And I was, yeah, that was a little bit, I was a little bit ashamed of that because actually the first 2 sections are, they're already an expansion of an appendix by Berlinson. So if you know Berlinson, exceptional mathematician, very good intuition, very impressive, and doesn't write a lot of detail. So he has this appendix, and this appendix is like 3 pages long. And it defines these things called filtered triangulated categories and like gives some properties of them. There are no proofs because he says the proofs are easy. The proofs have been written later by somebody else. But anyway, so what I wanted to do was take this appendix and write all the results, but not just the results of the appendix, but write the things that are implicit so that then I could look at these statements in the 3rd section and just write full proofs of that, just from the results that I had put before, so that the referee would be satisfied. And the referee was satisfied. I was quite happy with myself. And then I tried to, well, formalize, do that in Lean, formalize the definitions and the statements from the first 2 sections and see if I could formalize the proofs of the 1st section. And how did that go? So let me show you. I don't know. Can you? I don't know if you can read anything though. Is anybody here? Can you read anything here, or is it too small?
We can sort of make it out, I think.
Okay. So the first thing I want to point out, because I saw a talk. Well, there's this lecture yesterday. It was a very nice lecture, but the speaker said, well, what's nice in Lean is that every definition is computable. Well, so here, this non-computable section means I don't care about computability. Stop asking me. Stop telling me that fixes are not computable. I'm going to use the axiom of choice all the time. Yeah. So if you don't want definitions to be computable in Lean, they don't have to be. That was my point. Okay. So here's the start of the appendix. There's like all that, a lot of notation, and then it starts with some definitions. And so that wasn't too bad. Yeah, so I wanted to get here. Maybe I can indicate, whoops. Okay. Sorry, there was a lot of sunlight, so I closed all the shadows and it's very dark here. I cannot see, I cannot find anything, which is annoying. Anyway, but here's the definition, and this definition I have to do a few declarations before, but this definition is not too bad to formalize. So that's Beilinson definition. I just copied it. Yeah, nice. And then actually it's a very long definition, so I just formalized it in, so this is blah blah blah. I mean, then you have to declare a lot of stuff in it that you don't have to declare in math. So the definition goes on like 200 lines later, I can get to the second part of the definition, which is okay too. It just says like some composition of morphisms is equal to some other composition of morphisms, maybe okay. And then the third part, already here you have an isomorphism. Since you have a natural isomorphism in category theory, it has a technical meaning, so it does mean something. However, this thing here, so this thing here is a problem. Because you don't just have an isomorphism, it has to satisfy some properties, and these properties are not spelled out. And the way Beilinson writes it, by the way, is with an equality sign. So he writes I composed with phi equals phi f composed with I, which is what I was writing. Well, I was using T instead of phi, but so he writes an equality. Equality means canonical isomorphism. Canonical isomorphism means compatible with everything that I want it to be compatible with. But in ENS, you cannot do that. So in ENS, you have to tell what this thing is compatible with. And did I do that? No, because I just discovered that issue 1 hour ago, because I'm still discovering issues with that. Okay, then there's a bunch of results. So that and we're still in the definition here. So here we're at page line 420, and I can finally start stating this proposition. And so it says a bunch of stuff exists. Okay, great. But what I want to, because well, it's almost 11. So what I want to show you is well, there are some problems here. I'm a bit ashamed to say that the problems are mostly in the stuff that I added. So the first 3 statements are from Beilinsson's paper. And again, there's no problems with this. They're formalizable pretty easily. The 4th statement I added, I added because it was necessary for what what I was doing later, and Beilinson didn't write it because it was just so obvious. And this, well, it says we have canonical isomorphisms, equality sign. Again, this is just not going to fly because first, well, it says something like there exists. Where did I put it? Yeah, I hid it in some structure, but it says there exists an isomorphism here, there exists an isomorphism here, but actually, these isomorphisms are not arbitrary. They're actually given by the data that we have before. So what this should actually say was, we construct this morphism in such and such a way, statement is an isomorphism. Okay, so this statement, again, not formalizable as this. And I'm maybe not going to go through the whole appendix, but some more definitions. So this one's okay. This proposition, like everything has a problem. Again, you see there are equalities. There are isomorphisms. There are some more equalities. Everything has some. Actually, all of these are explicit isomorphisms. You have to construct them. You can't just write there exists an isomorphism. Like that's not what this proposition should be saying. And the worst offender is this one, this proposition A18. This is absolutely awful. Again, this one it's not in Beilinsson's paper. I added it because it was needed. It says these squares commute up to natural isomorphism, which means something is isomorphic to something, and again, the isomorphisms are not. are not arbitrary. What you should be saying is that some properties, so it's I think proposition, yeah, it's a total mess. It should be saying that, well, these objects have some properties. These properties imply the existence of some morphism, and this morphism is an isomorphism. And so that's what I had to write in Lean. So you see this proposition A18 in Lean is actually, well, pretty long. It's this whole thing. And that's without the proofs. There are no proofs in here. I mean, there are some definitions, but it's just because once you have one of these, then you have this one automatically. And the third one, I don't even know what the compatibilities are. It's not even clear, but not to me. Maybe it's clear to Berlinson. It's not clear to me. Okay. So, right. So now I just want to go to the new results part, because I said that the goal was to try to write proofs, 4 proofs of the new results. So did that work? And I say, well, okay. So there are 2 big statements here. There's this lemma F1, and there's this proposition F2. So lemma F1 is the easy one. So lemma F1, well, it basically just says that some objects are 0. So that some objects that are constructed in maybe complicated way are 0. And being 0, well, for an abelian group, if you want to say that a group is trivial, an abelian group is 0, again, that's not an equality, it's an isomorphism. It means it's isomorphic to the trivial abelian group that is just the singleton 0 with the only possible operation on it. However, the situation is nicer because there is only one possible morphism of groups from a group to 0 to this trivial group 0, or from 0 to another group. So if you have an isomorphism between an abelian group and 0, then it's automatically unique. And that's the same in every category with a 0 object, which is the case here. And so saying that something is 0, that's one case where you can write an equality. Here's an equality, like something is equal to 0. And that's actually should be an isomorphism again, but that's the least wrong of the equalities. So this lemma is just saying some bunch of objects is 0. And so formalizing the statement is quite easy. Formalizing the proof is a bit of a complicated calculation, and I really wanted to formalize that proof because there are some there's some game with indices exponents here. If you make one mistake, then the whole proof fails. And the proof actually that one is fully formalized. So it's that file. I mean, there are a couple stories, but the stories are because Masslib was updated, this broke the proofs. I mean, like it was compiling like 3 months ago that Masslib was updated, and I didn't find time to fix the proofs yet, but it was compiling. But the file is almost 700 lines long. I mean, we've seen that phenomenon before. So that I was very happy about that, because that's the technical thing that makes the next proposition work. However, the next proposition is, well, I formalized the statement. And you see the statement in formal mass is long. The statement in Lean is longer. But when I started formalizing the proof, I realized that I hadn't actually put every necessary result in the first 2 sections, and I'm in the process of adding them. So only the good thing is that trying to think about how I was going to formalize the proof, I wrote it down in a lot more detail, and now I'm at least convinced that it's correct. But I still want to finish formalizing it, so I think I should wrap up. Yeah, so did it work? I mean, it did some stuff that made me happy, but it's not done yet. And it just made me realize that I don't write as rigorously as I thought I did. Okay, and so the conclusion, one of the points that I wanted to make is that, even if you don't care about the proofs, they're formalizing statements. And that's not just category theory. The category theory is, I guess, maybe, well, I was concentrating on category theory. And so that's very prevalent in category theory. So that formalizing statements, that's not easy because the statements, they are often not the actual statements. And the actual statement is sometimes hidden in the proof or it's hidden in the context. And if you're not lucky, it's not even there. It's just like obvious to an expert. And then in category theory, many statements are actually definitions. So well, I don't have time to go to the lead find again, but a lot of things that in the article are like such a thing holds, actually in lean there are definitions. We say some objects are canonically isomorphic. No, you have to define the isomorphism. You have to state its properties, etc. Well, infinity category theory, from what I saw in formal mathematics, and maybe I haven't read the best authors, I'm sure Emily doesn't write like that, but some people are just extremely careless, and it was even worse than these are all one categories. So they're at least equality of morphisms has a meaning. Infinity category, equality of morphisms, again, you don't want to write equality of morphisms. You don't want to write equality of anything. And yeah, so I mean, so I want to talk about, we're talking about auto-formalizing mathematical statements and all that, and I want to say it's not clear to me how, at this point, how to do that with some fields of mathematics. Like, it takes a lot of work just to actually write the statements that we mean. And I am not sure how a computer can do that without input from an expert for now. And I don't know if, I mean, of course you want to tell people, and I tell my students that you should write more clearly, but when I'm not even able to do it myself, I'm not sure it's reasonable to say that people should just write more clearly. And that, well, yeah, that was the conclusion. So thank you for your attention.
So if there are questions, I'll pass over the microphone to make sure that Sophie can hear us. So are there other questions?
Thanks for the very interesting talk. I just wanted to try and understand if I've got your conclusion correctly. It's that it's super hard and not that useful. Would you say that's the right understanding?
No, I think formalizing these things, I think it was very useful. The project I did is just that it's already super hard. That was my own paper. I knew what I meant. Well, I thought I knew what I meant. It's super hard to just even formalize a statement in a way that it actually states what you needed to state. And so there was this talk this week about auto-formalizing statements and what the problems were, and I thought, well, actually there are a lot more problems than what was said. It's not just checking that the statement is not just that there are several ways to write the statement. It's just that sometimes just the statement on the nose, the statement is just not saying what the mathematical reader will understand. Well, okay, I mean, some papers just are not written well, but like even if you try to write them well, the statements they're just not self-sufficient. Like part of the information of the statement is hidden somewhere else.
Thanks. Just a quick follow-up. I think at the end of Floris's talk also, we had this question. Is there any kind of tooling or something from the software engineers that would make things easier, better, that immediately comes up to you?
I mean, my biggest problem now is library search. Like knowing what is already in Mathly, like looking for already formalized statements in Mathly. So that's and that has improved a lot in the past couple of years, and I think that would make my life easier. And I guess I've seen some things that, I mean, sure, a tool that could auto-formalize a mathematical statement written very, very clearly would be useful too. But the biggest thing that slows me down is just library search. Like, you have a statement in your head, it's written in, mathematical terms. You don't know what it's called in Mathly. You don't know how people described it in Mathly. How do you find it?
Hi, Sophie. This is Emily Real.
Yeah, I recognize your voice.
Okay, that was a great talk, and I just want to reinforce the takeaway for me, which is this point that you just made at the conclusion, which is just how valuable it is to an active researcher to try and formalize the definitions and theorem statements in their work, even if it's completely impossible to formalize any of the proofs because of the background mathematics or anything like that. And I mean, something that's certainly been part of my personal experience is I feel like I'm able to think a lot more precisely about the meaning of, what I mean by a definition or a theorem statement now that I have some experience with type theory and with formalization. I think there are a lot of things that are in practice not articulated very precisely in sort of set theory as a foundation system that are much easier to state precisely in type theory. And I do think some of that has to do with, constructive aspects. So as you pointed out several times, that the correct interpretation of a lot of theorem statements in category theory is that a specific map is an isomorphism rather than there exists an isomorphism. Anyway, that was kind of the main thought. And then in terms of the resolution of the many different meanings of canonical, the way that I like to think about this is that canonical either means specified, so that I think this is something like your Bourbaki meaning, but perhaps unclearly specified. So I would urge folks who are using canonical in that sense to, perhaps replace it with specified, and even better specified here as opposed to specified in the abstract. Or it's in the sense of something being natural in the sense of category theory, and then you need to clarify exactly the meaning of natural. Is this a natural isomorphism with respect to certain types of maps or something like this? And I think that certainly covers the double dual example that you mentioned, and also many of the uniquely existing isomorphisms are characterized by natural. But anyway,
I mean, there's a statement I didn't have time to show where it says, something exists and it's unique up to unique isomorphism, but when I formalize it in Lean, the unique isomorphism has to respect some structures, and you have to actually think a little bit about what these structures are. So this, so this, that's related to what you said about, when you say natural isomorphism, like natural with respect to what kind of maps. To do non-category theory, like natural has a precise meaning in category theory, but the meaning depends on some context, and the context is not always specified.
Hi, this is Deirdre Haskell. I wondered if you thought that or what you think about, are there parts of mathematics which are more or less guilty of being vague in the way they make their statements?
I'm not sure which parts of, I don't know all parts of mathematics. I've seen a lot of vague statements, and what parts of mathematics do you mean? Because I might just not be familiar with them.
I just wondered whether you had a sense of, in terms of reading general papers, kind of across a bunch of different disciplines, whether some people seem to be being more explicit about what they mean when they say something's isomorphic, or when they make a statement about things being equal, whether there's implicit knowledge that's going in there. Of course, there's always implicit knowledge that goes into writing down the proofs, but and extracting some of that implicit knowledge is part of what's going on in formalization. But there might be some parts of mathematics where it's just more clear what we mean when we say that things are equal, and other parts which are less clear about what that means. But maybe you don't have an opinion on that. It's okay if you don't.
Yeah, I mean, like if you're, you know, if you're working in something, like if you're working in a analysis or analytic number theory, you write that two numbers are equal. That has a precise meaning. You're working in category theory, you write that two objects are equal. That doesn't have a precise meaning. But I'm not. I don't know if there are some parts of mathematics where people are less careful about their statement. In my experience, it's just like some people are less careful and some people try to be more careful. And I've always tried to be careful, and what this experiment has taught me is that I'm not careful enough, apparently, so I'm not sure I'm the best one to judge. I mean, certainly there are some papers that have gotten me very angry at the authors, but I don't want to name any names here.
Yeah, thanks for this really nice talk. I asked this question as a non-mathematician, non-lean expert, so forgive me if it's not the greatest question. But in terms of formalization, is the challenge in formalization to some extent that humans think differently from how dependent type theory thinks? Or is there a way of thinking that we could somehow, like, it's kind of building on the question that was asked about how software tooling could help, but is there a way we could encourage humans to think like dependent type theory? I don't know, maybe this is not a good question, but if you have any thoughts in this direction. And the second related question would be, do you think it would be easier to work with a badly, like if you write something in natural language, then you try some kind of machine learning based autoformalizer, it autoformalizes it badly, and then you have to correct it, versus just starting from scratch? It's unclear which is easier. I was wondering if you had any thoughts on that.
So the first one, I think actually, well, if you compare type theory to set theory, which is what I was taught as an undergrad, set theory, I mean, I think type theory is actually more natural. It's closer to the way we think. So I don't think the problem is well, I only know the type theory of Lean, so calculus of inductive constructions, I guess. But I don't think the problem is type theory. I think the problem is just this humans. I mean, that humans just take shortcuts and just don't want to write too much obvious stuff because the obvious stuff is boring. Like if you write down these full definitions in category theory, like unless that's your a specific kink, which is, it kind of is mine, but I think for like a normal mathematician, it's very, very boring. I'm not sure what to do about that, but it's not type theory's fault. And okay, and maybe you should ask Emily this question, because I saw a talk by her about how if you understand this homotopy type theory, that might help with infinity categories, but I don't understand homotopy type theory, so that shouldn't ask me about it. And I'm sorry, so this is the second question was, yes, I remember the second question. Well, it depends how you're informal mathematical text, how close it is to what you actually want to formalize. Because with some of these statements, like for example, this proposition A18 that I wrote in the Lean file, is just everything is wrong with it. Everything. It's a total mess. If I auto-formalized it, I would just have to scratch everything, and you have to start in a completely different way. So I think it could have some value, but you have to think before about how you actually, what you actually want to say, how you actually want to formalize it, and maybe you write more precise informal mathematical statement where you don't have all the details yet, and you try to also formalize that, and then you can use that. But there needs to be some more work on some of the statements before I think that can have value.
Sophie, I think after thinking about all the challenges you've raised, I think we all need coffee. So let's thank Sophie one more time. Let's do the coffee break. Thank you again, Sophie.
Okay, see you guys.